Hi again, this is Claudio from expertfea.com. Today we are going to simulate heat dissipating due to friction in contracting parts. So you have seen the trailer that I've shown. Let me firstly share my screen. So the trailer was the simple case, this one with one disk, and further on, a little later on, we will simulate this scenario. So firstly, let's begin with something much simpler. Let's say this is the simulation for the YouTube clip that you see. Let's firstly start and simulate something simpler and show how it's not possible to be made in a static structure or maybe even transient structure, I think. So let's drag and drop a static structure. And here we're going to model a simple geometry with a piston in the cylinder, yes, and we will have only a reciprocating motion, a translational motion of the piston in the cylinder for an internal combustion engine. Now space claim is being opened, hopefully. We'll model something very basic, let's say. Let's model firstly the piston, yes, 30, I don't know, maybe 150 millimeter, okay? I said this will be the piston, all right? So let's do something like this, 140, 40. How much should we go? I don't know. 100 is enough. It's just for tutorial purposes, all right? So it needs to be kept somehow, to have a cap, yes? And let's go here, design fill. So this face is filled, and we're going to pull with, I don't know, maybe 5 millimeter, something like this, all right? And you can see it. It's something very basic, because in theory you are interested only in the contact, in the heat dissipated between this surface and the inner face of the cylinder. So again, I think we can copy paste this, triple click, Control C, Control V, yes. Let's change one, let's hide one of them. And we will drag this one in order to achieve a cylinder. This is the cylinder, all right? But the cylinder will have, in this configuration, the same height as the piston. So we need to make one of them longer, let's say, all right? So I'll make this a little longer, not too much. And of course, different diameters, yes? So let's make the outer cylinder how much? Should we displace with, yeah, 80? And here inside, of course, I need to select here no merge, all right? Or else by default it will merge. with the other parts. So 80 here, and maybe 75. Does it work? Yes, it kind of works. Let's go in the section view to see how things are. Look, something like this. All right. We would like for let's name them. This one is piston, and this one is. We should maybe move the cylinder something like this. It may be extend it a little, all right? Let's extend this face a little more. With move, if we extend it with move, there will be no merge. We're dragging this axis, something like this, all right? Let's save and let's save the entire simulation. All right, save. Also, the geometry is going to be saved. Let's salute if we have any spectators. Let's salute now. Yeah, maybe they are, but they are too shy to say hi. I would like to point out one thing. The one thing being that we have zero gap here. So in theory, in practice, we cannot have a zero gap, yeah? This means that we need to leave a little allowance, a little gap, all right? Let's see how. We have, if we click pull here and drag this, we need to make it a little bigger, but how much? Out of curiosity, can I learn how much is the gap? Gap between piston and cylinder. 0.025. All right. Now my question is this on diameter or on the radius? Do we have an image? Yeah, nothing interesting. Let's make it on radius, all right? 0.025. So we can hit now and maybe. Yeah, let's go here and write 75.025. Now we'll have the needed gap. Look here, this is a gap, all right? And between these two parts, we will have a frictional contact. Even though we know that in reality we have oil, yes, which lubricates this entire assembly, and the tightness, I'll say, okay, is the burning chamber, let's say, the combustion chamber is sealed with segments, okay, or how are they called in English? Rings, I think. Yeah, piston rings. Yeah, these ones. Compression and oil control. All right. So these will ensure the tightness of the combustion chamber, and yeah, at this moment we're going to adopt a simplified simulation. All right. No rings. Yes. We just want to prove a concept. So this is all. Of course, I don't want to make the rod, the crank, and the crankshaft. Let's name this piston and cylinder. I already have defined some, or not. let's bring the materials that we have from here, or you know what, let's leave default. Because firstly, I would like to prove that it does not work by default, all right? That more work and refinement needs to be done. It takes a few seconds because I closed the space clean. Zoom extends F7. This is zoom extends F7. So we have the gap. We have the material still by default. Let's see the only contact, okay? This is the cylinder and this is the piston. All right. Right-click rename based on definition. Of course, we'll not be beginners and leave it bonded. Frictional. Let's see how much. Can we? I don't know if we can, because in theory there is some lubrication here. Come on. Piston rings and cylinder. It should be, yeah, it's something 0.15 on the lubricating. You know what? Because we need heat to appear, let's kind of double this value. Let's make it 0.3. But yeah, in theory, in practice, it's well lubricated. All right. So let's make it, just for the sake of this simulation, let's make it 0.3 in order to ensure that heat will appear, hopefully. And what we had, I think, for detection method, we need to have, let's leave everything program control at this moment. Right-click generate mesh. Also the Control B, let's assign a sizing for the piston. I meant not sizing, but a method. I would like, if possible, to also be hex. Hex dominant, all quad. Let's see if it works. It should work because it's very simple. Yeah. If I choose use adaptive sizing, no. Let's see what will occur. Yeah, it works. So this is a small trick, yes. Instead of yes, make it no. The sizing is a little too coarse for my taste. This means, can we assign a general sizing of, instead of 14, maybe 10? Maybe 10. Let's see here. Why wouldn't you work? Come on. So we need to go with default. You know what? Let's go with default, no problem. We have other things to do right now. I'm running a no-go scenario, yes, in which we'll use everything as default. How much time does travel the stroke occur? Let's see how long. average stroke time. I don't know if it will. Of course not ischemic or cardiac stroke. Average stroke in ICE engine. Yeah, there are 4 strokes, and we need, I think, to have some calculations. Come on, how much should it take? Look here. We have a mean torque crankshaft. We don't have time here. Where can we have some timing for the stroke? Come on, no timing. This is the angle of the crankshaft. Crankshaft torque of each cylinder. Angle, yes. They don't care about time. Maybe here. No, they care only about cycles. So let's end time should be 0.25, okay, something like this. And you'll ask yourselves end time of what? So let's assign like a displacement for this. Displacement I would like to scope phases that do not interfere in the heating and in the contacts. So in the contact. So let's displace these 2 phases, all right? Let's displacement on the y-axis with the value. I'm looking at the ruler here, and a value could be 60 millimeter, okay? On the y-axis, minus 60 millimeters. Do we need displacement or x? No. On z, no. We only need this displacement, axial displacement on the y-axis. All right. So we have a displacement. Let's fix. Let's fix the cylinder. Should I fix it here? Sincerely, I don't want to fix it here because it's too close with the contact and the heat dissipation. Let's fix it here and here, all right? And ladies and gentlemen, we have a very quickly defined scenario, all right? I don't think we will need 50 cores, but you know what? Let's make let's leave it 50. So we have this, all right, save, and let's solve. Just as an example of it does not work, okay? This is an example. This is default, friction, and simple translation here. So it solved in 5 seconds. And let's see, all right? The scale was minimized, something like this. So we have this displacement. Let's make a section view, new section plane. something like this. You see something occurs, yes? There is also some stress. The values are very high because we have linear steel. The mesh is awfully coarse. Let's leave it like this. All right, so we're investigating if heat dissipated. All right. How can we see heat? Heat usually is seen by accessing worksheet. And here we're looking for BFE. It's not an item called temperature, but it's called BFE, which measures temperature. BFE, look, this one, all right? So if you drag and drop, you can see here already temperature, the output unit, all right? Create user-defined results, right-click, evaluate all results. Yeah, no heat. No heat, yeah? This is the default, it's just a translation. The translation, nothing happens. Because I would like to reuse this scenario, let me think a little if I can convert it to a different type of scenario. Yeah, so it's a straight line, it's flat, it's 22, all right? Because I was thinking maybe if we defined more cycles, I was thinking maybe heat will gather, will add up, and it's not the case because the value is 22. If the value was something else than 22, we would have had a temperature buildup with some heat appear, all right? So in this case, by default, the heat does not work, all right? So let's close this scenario. And let's use, of course, heat can be made to appear with the APDL commands, okay? But I would like to teach you the quickest ways, let's say, yes? And at this moment, this tutorial is for beginners, let's say. So we're not going to work with the APDL commands anytime soon. Let me close this. And maybe, you know what, maybe duplicate it. Let's see if we can convert it to the scenario that I was proposing. I was talking about using couple field transient, because here we can we can corroborate the structural side of the simulation, the thermal side of the simulation, yes? So here let's, because we don't really care about the simulation, let's see if I can replace with coupled. No, it's not possible to replace it, but maybe I can. Maybe I can save at least the geometry. Let's see if I can do this. Sincerely, I would like to delete the, I cannot delete this. Or can I delete this one? I'd like this not to disappear. Let's see if it works. Oh, it stayed, all right. So save, couple field transient, all right. Let's use also default. Do we have any salutations in the chat or question? No. Perfect silence, all right. So it looks like a typical static or transient structural simulation. We'll leave the default steel, because usually the default steel has some thermal, look here, it has some thermal properties. Also thermal conductivity, specific heat, constant pressure, and so on. The contact here also is left by default. All right, so physics region. Yes, on structural, yes, on thermal. We're good with this. What other loads should we have? Maybe define it, or we'll run it only for one stroke at this moment. What we need to apply, again, we need to apply that displacement. Apply on the y-axis, and I remember it was minus 60, yes? 0 and 0. What we need to apply? More. Another, let's fix, another fixation. Control pressed, fixed on the cylinder, and let's assign just like as a reference. Let's assign a reference temperature 22. I think it's kind of mandatory in these simulations, and an overall convection. Can we look just for fun? So it's called film coefficient, yes? Let's ask Google about a film coefficient. Usual film coefficient in ice engine. It's in cylinder, 100 to 100,000 and more watt per square meter Kelvin. In order to have this measurement unit, let's change here to this one, I think. Yes, and the temperature to Kelvin, yes. Look, watt per square meter Kelvin. And how much should we assign? It said something like between 100 and 1000, so let's meet in between. 500. Where? Everywhere. So Control B, I will select one part and also one part. Yes, we have like a film coefficient. And the temperature, this is the 22 degrees Celsius. It's now in Kelvin, all right? Because we have obtained this measurement unit in a very easy manner, we can now disband it. We don't need it anymore, at least for me. For me, it's easier like this. Let's see if something occurs. Okay. Solution information, deformation, stress, strain, and temperature plot tracker. Switch to automatic mode. Again, deformation, directional. We will have velocity, strain, and stress. Will we have some equivalent plastic? Let's see. Thermal, we need temperature and total heat flux. Yes, we have output, solution output here for thermal. We don't need to go to the worksheet button, yes? This type of simulation is dedicated to incorporate more physics domains. Save. Let's see what happens for one stroke, for one travel, because I think I will need to define more strokes in order for the temperature to build up, all right? think it will solve very fast. Yes. We have force convergence, and here we have heat convergence, also heat convergence, and it looks very, very nice. The solving takes more because we have multiple physics domains, and we have very coarse mesh. This is very coarse. Very coarse mesh ensures a very fast solving because we need results on the go or live to keep the audience interested. What's happening? Yeah, sometimes we don't see results, but this occurs, I think, 1 in 10 times. Sometimes they don't show the live results. We do not care so much because we're close to the finish. So everything default here. Let's see what we have with everything default. Let's check that the animation works. It does work, but of course, I didn't make this 0. Let's make this 0 in order to have a gradual increase, right? So it's from the very beginning, it went to 60, right? It's an oversight from my side. I apologize. So it would be very nice to investigate braking simulations. Let's see what other people have done. Thermostructure. So now it goes gradually, all right? We have this one. Was it enough time for some heat to be dissipated? Let's see. Also, we'll check with some strain. There is no strain on the cylinder. The cylinder is not impacted at all, all right? No temperature and total heat flux, all right. So, by default, without interfering too much, it didn't show many things. I sincerely want my first step. I sincerely want to increase from 22 to something, because now it's clear that there is no dissipated heat. Let's see if you can see my legend. Can you see my legend? I don't know how. Okay. So it's something like this. My legend is here. I hope you see it. I would like to have some different values here. So a thing that I remember that works, we should have detection method nodal normal from contact. And just for fun, let's increase a little to ensure very high friction. And what can we do here? Maybe make this direct. And yeah, let's solve it. Let's solve it. It can be that the gap that I modeled, maybe it's too big. Let's see. And also, let's also remember to refine the mesh. Yeah, nothing. All right, so let's refine the mesh. How can we refine it? I would feel confident if I have a smaller gap in order to ensure that the faces touch. So this face had a diameter of the radius 75.03. Let's make it 0.01. 75.01. And we'll have that gap. I can show it to you. Design, section mode. Look here. Yeah, this is the gap. Let's hope it's enough. I'll go here, right-click, update geometry from source. Save. Do we have something wrong here? Let's see. Physics both, displacement yes, fixed support. We should always check the boundary conditions and the contacts after the geometry was modified. Solve. So we can look also here. Heat flow convergence, displacement convergence, line, such parameter. Yeah, everything looks nice at this moment. Let's see. Oh, nothing. All right, so let's decrease the gap even more. $75.001. And even though the software rounds the value, I think we can somehow measure the gap. Let's see. Click here. Let's exit the command, the poll command. Click here. Then with the control pressed, you can scroll with the middle mouse. When you scroll, you are hovering through items. And now I selected also the inside. Look here. This face and the outer face of the piston. Yeah, I selected these two faces, and I'm going on measure. And you see here, there is this gap. So let's leave it like this, save, and see if it works. I'm wondering if I should have the contact side, the inner face of the cylinder. I'm wondering. All right. It looks good. Yeah, hopefully it will work. I have done something with piston and cylinder a while ago, but it was with it was made with the APDL commands. This one, and we had more strokes. Here, having more strokes, you can see the temperature build up. But this was made with the APDL commands, and I would like to make it. Oh, we have some temperature. We have a heat flux. What happens when we flip contact and target? Let's see. Maybe I was wrong with the contact side. Of course, in your practice, in a project, in your laboratory, you'll use the proper values, not the ones that we invented here, that I invented here. We begin to have heat. Yes. What can we do to have a finer sizing? Instead of yes, what will happen if we choose no? Instead of no, yes. Come on. Does it work with sweep? Why? Why should it work? All right, multi-zone it is. Method multi-zone. And it's kind of guaranteed that it will work because it's such a simple geometry. Yes. So let's make the same sign sig for both parts. Because we're here, let's define at least 2 strokes, all right? The end time is too slow. I forgot to modify it. 0.025, let's make it, and here 0.05. This means we will need to adjust some values. The maximum time step can be 0.01, and the minimum can be like this. Here over time step, why not? 1, even though it doesn't show it's on. It will carry the time step from one step to the other. Initial time step, 0.01. All right. So let's now make it 0. So it goes down, then up. Yeah, let's leave it like this, you know. If nothing occurs, I will also edit the convection coefficient value because it gave me a range. And I think I will need to decrease it a little. Save, solve. It works. So this was made 12 years ago, all right. In transient structure. Static structure, not interested. Let's see something with heat. Here we see only the rod being loaded, so we're only interested in what happens between the piston and the cylinder. Transient, no. Terminals, let's see what we have here. It's a thermal simulation, so there will be no heat dissipated due to friction only. And the temperature, 720 degrees. All right. For fun, let's see the average temperature in ice engine. Piston, something like this. There was a piston temperature from 200 to 300. Yes, this is why when I see here 720, I have my dots here, so it's kind of too much, I would say. So now I think it will work, these results, the live results. Hopefully. Yeah, they work now. Let's go here. This is where is our interest. Yeah. Yeah. So we have something. And we're in the beginning. Yeah, let's wait. For fun, what is the average? I've seen the average gap between the piston ring and the cylinder, 0.001 inches, if I remember correctly. Okay, let's see this. Convection coefficient, what value did he use? Come on, you can select all with Control A. Or, all right, let me see the value. 320 watt per square meter. Watt per square meter. Square meter Kelvin I need. Let's see if it will converge. It will convert. Ah, it's the same, of course. But I remember that we had different values. We had very small values, not this one. All right. At least it displaces, yes, it displaces. And temperature, do we have temperature? We have some temperature. It's not so much. But I think we might have some temperature. Yeah, the temperature and the convection coefficient is too high. Temperature. Of course, because you applied 720. And I think this is too big, I think. Too high. All right, nice work, besides the values. Piston practice, let's see. You have a kind of chunky rods instead of country roads, chunky roads. ANSYS projects for mechanical engineering. Oh my God, such a mouthful here. Transient model, yes. No, I'm interested in heat. Transient thermal analysis of piston. The same. Here you can maybe read temperature and convection, so it's the same that we have seen before. Moving piston ANSYS fluent. I want to see moving piston ANSYS fluent. We have an increasing value above 22.2. Maybe we need more strokes and to decrease the coefficient. We will see. Transient simulations take a longer time, longer than static, and longer than explicit dynamics if the explicit dynamics are not if they are not quick events, yes. So I mean, if the explicit dynamics simulation is analyzing a long event, then it can take much time. It depends also on the mesh density and so on. Structure rectangular mesh, 0.1 meters per second. So here is the, I want you to show the hand. Here is the piston and here is the combustion chamber. Between the top of the cylinder and the top of, and the piston head here. Yeah, the piston as it's advancing to the peak point. I don't know, peak of the stroke or something. Very nice thumbnail. ANSYS FEA piston modeling. Okay, piston ring design. It's a ring. What philosophy is this? It's just a cylinder that you need to cut. Static structure and transient thermal analysis in the piston. I'm not interested in thermal analysis because you just insert the temperature. So cod monkeys. Thermostructural coupled analysis of piston in ANSYS workbench. He firstly makes thermal, then he will see the dilations, the deformation, the stress, and in a static structure, I think, maybe. Let's see. We're past the half of the FEA. So I think we begin to have some heat being dissipated. Let's wait and then adjust this, modify this. Let's make it 1e minus 4. And if we're not satisfied, we're going to with 10e minus 4 or something like this. You know, if others exaggerated their values, why not? Let's also do it. Where were we? Steady state thermal. So he assigns the same 320. Come on, no, please, no, not the same. No. All right. So he's applying a static, yes, and he will. He fixes something. All right, the bolt holds. A pressure, why do you apply pressure? Because you're also copying. You're also copying something from the steady thermal. All right, Buster, but can you show me also temperature? Static. He doesn't show the scale. Look at the scale. 10. Why? Why do we need to have scale 10? Yeah, very simple work. Yeah, something like this. We do have something, yes? There is some heating here. All right, thermal seasonal piston ring, yeah. Temperature and heat flux, all right. Real life application. That's a transit structure analysis. At 3000 RPM. This I would like to see. 3000 RPM. Oh, everything is rigid besides two rods, two connecting rods. Everything is rigid. With rigid parts, you quicken the FEA, you solve faster. He wants to say that there is this like a fatigue simulation. It looks nice, nevertheless. Yes. And do we have stress values? This is the common. This is 43. It's not 43,000 because the maximum is 2,400. He has such big values because he does not use nonlinear materials. It might be with the 3000 RPM because he has a very short end times for the strokes, very short cycles, I'd say. And yeah, it can be that he used 3000 RPM. And if he used this value for the rotational velocity, he used it here. Yeah, nice FEA. What is the purpose of publishing 11 seconds of nothing? Why? 19 seconds, nothing. It's real life application, yes. Tutorial 7. Mr. Pavel Taranenko. He sets the temperature, yes. Piston analysis, ANSYS FEA. I'm interested. Oh, yes. Yes. What should I do? I think I will make the mesh more coarse, I think. Because I'd like to have faster solving trials or iterations. This one is from 10 years ago. What is this? I think he's Vietnamese, I think. (2015), I think. Chair? Why? So this is a piston, I think. And there is some temperature, but it's not so nice dissipated. Let's see. Is this temperature? Average. I don't know if it's temperature, maybe stress. Oh, I don't know what it is, but it's so big. The power of 11 and 13. Oh my god. What is this? This is a piston? I have no more comments. Transient structure analysis in piston crank mechanism. All right. Let's see, 9 seconds. It kind of looks nice, but why filmed with a Nokia phone? Nokia 1100, why? Come on, why? Ooh, such a small assembly. I think it's from a motorcycle, or I don't know, the Monolore cutter or something. Oh, Hindi. Static pressure. Structure and thermal analysis of piston head. Explore precision engineering. Yes. What is this? Yes. This is something, an example of what I did yesterday with couple, Euler, and Lagrangian. So we have water being pushed. I will not say compressed because I know that it's incompressible, It's being pushed by the piston here. Engine block. This should be interesting. 3 seconds. Simulation is done in ANSYS. Let's see. 3 seconds. 1, 2, 3. It looks very nice, but yeah, we should have seen more. So it's going to finish here. Let's see in section what it does. All right, 1 cycle, let's say, all right. I'm not interested in velocity, I'm interested in stress. For example, something like this. Let's click update contour range at each animation frame. Yes. And because we have such transference of stress due to friction, then we surely will have some temperature. Yes, there is something. What I would like to do is duplicate this and modify the film coefficient for the convection boundary condition. Piston and cylinder 1. This is the first case. Duplicate. Do you have any questions? Yes, we have. I think it's our friend from Romania. Hello, Mr. Vasile. Thank you for the subject, thermal plus mechanical. Thank you for watching. Simulation and creating here a problem with resolved steps. Very educational, almost scientific. Educational, yes. It will become scientific when we have proper values, yes, and proper expertise. But thank you for the appreciation. Let me write here. Everyone needs encouragement, so I'm no exception. Should we interfere here or not? Let's not interfere with the geometry. We will leave it like that. But I wonder if I have a bigger travel. You know what? Let's make this piston a little smaller, something like this. Let's make the cylinder a little longer. But I don't think it does anything at this moment, because this is space claim opened from here. Let's just close it. Undo 1, undo 2. Let's close it. And hopefully I can somehow select not to update. You know what? Is this the new? Yeah, this is the new simulation. Where were we here? Double click. I would like to have a longer travel, yes? Longer travel of the piston. This the purpose of these live simulations is to attract beginners and to make the domain, let's say, accessible. My advice is for people watching, maybe do something similar. This is why I'm also modeling some things very easy, just a cylinder in a cylinder. It's nothing very time-consuming or difficult, and it opens the occasion for exploration. Just be curious, just very diameter, very gap, very modify material properties, modify film coefficients, thermal expansion parameters from the materials. Just be creative. Let's see in a section. I'm selecting an axis. Control S for save. I was thinking about making the grooves for the rings, but not today. It takes some time for the geometry to update. What is this? This looks nice. Yeah, it looks nice. Mr. Bharata, our Indian expert. Slow motion. Come on, who has time to wait for slow motion? Yeah, it's promising. Does he have something more? 13,000 subscribers. Oh my god. Oh, he has worked. Monosuspension system. If you're working in static structure, why do you have streams? He didn't change the thumbnail. Terminal says on PCB. This should be interesting, but I won't look now because I'm interested only in cylinders and pistons right now. So we have the update. What I've overlooked, I forgot to change the material properties between these two. Instead of right-click name based on definition, instead of 7, I don't know, can I make it 9? Yes, I can. I was suggesting to modify this to 1e-4 and see what will occur. All right. Should I increase the friction coefficient or not? It changed the default contact, yes. So let's go again to frictional 0.5, and here we had, for detection method, we had nodal normal from contact. Was the contact like this? Maybe it was the other way around. Let's see. All right, physics region correct, displacement correct, fixed support yes, temperature yes. Convection, yes. Let's see if it goes faster. Can I deal with some things here? No, let's make this one like this. Initial time step, and here 0.5. All right, because we usually have convergence. All right. When we clearly have convergence, we can kind of exaggerate and increase the time steps. Save and solve. You can maybe ask, hey Claudio, why do you have such a big friction coefficient? If we're using a lower friction coefficient, then we would need to prescribe very, very numerous cycles, let's say, and we want to have live results, remember? So the FEA works very quickly. Let's see why, because, we're not used to it without obstacles. So he has made lots of lessons. Oh, 900 views. Oh my God, this is why he has 13,000 subscribers. Hi everyone, this is the channel that provides the example of the engineering project which can help to learn and complete your academic research. And I think here we can... he joined in the same year that I joined, 2013. Let's see his page. Oh, not available. Save. The FEA has finished successfully. Let's see what shows. Oh. Oh. I forgot to modify this. We should have had a longer travel, 150. Minus 150. Let's see if it goes. And maybe we need to flip contact and target. Let's see. If it does not work and we have no heat being dissipated, then we need to refine the mesh. Because I think maybe the nodes will not meet each other while traveling past each other due to the mesh being too coarse. The fact that the FEA is so quickly to solve maybe is a sign that it's not heading in the right direction. We begin to have some values for the temperature. All right. Explore precision engineering. Collecting geometry value. AutoCAD file pages. When was this done? 1 year ago? This is workbench. Come on. Who uses AutoCAD 3D? AutoCAD 3D? Nobody uses AutoCAD 3D anymore. Or, yeah, I'm sorry. Maybe some people use it. Maybe. Look at the film coefficient value. $273.45. All right, let's see his value. It's too high for my taste. So DFE finished. Let's save it. And let's check the temperature. Oh, we have something. So if we assign another cycle, what will happen? You know what? I like this. Let's assign another cycle. Here, let's make 4 because it goes very fast. So here we had 1e minus 3. All right. Let's make carryover time step on. And here 0.01, I think. Am I correct? Yes. All right. So minus 150 to have two cycles. Yes. Up, down, down, up, down, up. All right. Fix support again. Temperature. Convection. What will happen if I use 1e minus 5? Let's see, out of curiosity. Let's experiment. Safe. I will write down 1e minus 4 because if this value does not work, we will revert to what we had. Does the FEA run? If we clear generated data, then solve. Yes. Soon, very soon, we will make the simulation with the brake disc. It is important. It's kind of similar to this one, but is important because we have a rotational movement, and maybe you don't know it, but heat being dissipating when during rotational movement is pretty cumbersome, let's say. So yeah, we kind of need to see it. All right, I'm dusting my desk. I was here. Here, what did we have? But what was the load? The load was temperature and convection. 400 Kelvin. This means around 230 degrees Celsius. Finally, yes. He sees the effect of the thermal load. Only the scale is exaggerated, maybe 10, 20 times. So much for precision. All right, ANSYS piston. It does. I don't hear the fan going, so it does not work. This means I will need to stop if yes. As I said before, when we're using mini cores, the fans usually rotate much faster and they are clearly audible. Yes. Finally, it took off. Simulating a pin. Hyperelastic O-ring in ANSYS workbench. Hyperelastic O-ring. Yeah, this looks interesting. Something similar I have done maybe 7 years ago, something similar. ANSYS piston, PIM analysis. I think Mr. Mohendes, I think he's Turkish, maybe? Yes, I think he's Turkish. Do we have any question? Hello, chat. Yes. Hello, chat. Hello. Hello, Mustafa. Thanks for watching and learning. So at a certain point, on beginning with step 2, there is heat, yes? This is why I think I was inspired to create one more cycle of down and up, because now we have heat being dissipated. Let's see what other colleagues have simulated. This is pretty old, I think. 8 years ago, all right. SolidWorks, engineering data. I also should use such materials, and I have them defined, I think. Gray cast iron. Okay. Pressure. But where did he apply the materials? He doesn't show where did. For all I know, he has default steel. For all I know. Because he didn't show where he applied the material. Yeah, it's just a pressure, okay? So nothing too extraordinary. Basis of compressible flows. This was the FEA that I mentioned a few minutes ago, that I have done something similar. Maybe the colleague copied my FEA. He would not be the only one. Also, this colleague. What? All right, real life application. ANSYS workbench 04. Come on, give some details. ANSYS simulation of radial piston pump dynamic and static analysis, model analysis. Fitting rubber o-ring into cylinder and piston analysis. ANSYS Hydrodynamics. All right, where are we here? Ooh, we seem to have a loss of convergence. So it can happen that the loss of convergence is due to the fact that, for example, here, when we have too much heat, yeah, this one, they should dilate in principle, they should dilate in tandem. I mean, because it's the same material, the rate of dilation for here, yeah, between it, the diameters, all diameters will increase, all right? And being the same diameter, they should dilate in tandem. A small problem is the fact that the gap is too small. This is why we have rings to take this into account, and this is why we have different materials in order to ensure different rates of dilation. We have materials with different, in reality, we have materials with different thermal expansion coefficients. So normally, I think this is the problem with the different dilation. What I would test is with some other materials. 1 second, I will look on the materials I have used for the brake disc and brake pad. This is the pad, 1 - 5. It's also iron and yeah. So you know what? Let's leave it like this at this moment. Do we have any change if we have a final mesh? Let's see. steady state simulation of a diesel engine piston. Oh my god. Student project. All right. Music. Lots of simulations. I always congratulate work. I respect work. Do you like so much this font? All right. Oh, I think he has some rings. I think, yeah, he has rings. Perfect. Temperature. How much? Do we have value? 365. A year of temperature. What value? I will check the smartphone for a second. I have a message. Please excuse me for a second. All right, I replied. What does this do? We have some heat. Let's check a little. Piston material in ice engine. Okay. Aluminum, silicon alloys, aluminum. All right. And the cylinder. Cast iron. Can we make this? Why not? Let's assign. Let's assign this after the FEA stops. Should we wait or should we not? No. So gray cast iron and aluminum. The cylinder was made from gray cast iron and the piston is made out of aluminum alloy. All right. Let's go back to a higher value in order to ensure a quicker solving. What value did he use? Come on. 100. Maybe we should also use such values. Why not? Shows the temperature. What? 365. Yes. As a reminder, film coefficient ANSYS engine. It was no formula, please. $100 and $1,000. Yes, these guys are right. Piston thermal analysis. How to model an engine mechanism in 20 minutes. Yes, it looks nice. Mr. Sarjun, an old collaborator. How to design a piston units on cryo. Our friends from ANSYS Romania, ANSYS dealer in Romania. Rigid body dynamic. Why did it stop? Oh. You know what? Let's make it 1,000 just for fun. Then we're moving towards the disc brake simulation. In a message, no additional message, and we are approaching the 2-hour milestone for the live stream. ANSYS thermal combustion. This is a valve. Does it work or not? No. Will you stop or not? Control Del, Task Manager. solver is maybe this one, maybe. Let's see if it's this one. See the speed. All right, why does this not stop? Why? Let's give it a rest with the piston-cylinder, and let's do the disc brake. We have experienced too much for today. So I will name this disc brake. I think disk is like this. We don't really care about these two at this moment. And here, I'm going to inherit no, let's not inherit at this moment. Let's use here the material properties for disk and brake. Mechanical properties. Brake disk. Cast iron. So we will use iron, the default that we have in ANSYS workbench, cast iron, and brake pad material properties. Yeah, it's pretty complex, I would say. Look here, something very simple. Let's copy this one, right? So duplicate, and here I will name it pad. The density is 2700. Coefficient of thermal expansion. Do I see it? I don't see it. I see a specific heat. Specific heat, constant pressure. All right, 4000. Thermal conductivity, 2.36. These values I do not need. I will will leave this default. Poisson ratio 0.29, why not? The Young's modulus 28 gigapascals. All right, this is the pad. The geometry. I will take the geometry from another simulation. Delete the connection. Then we're going to make the simulation, the setup. So when testing various geometries and simulations, we can go so far with improvisation. Normally, we need to have the proper geometry, the proper gap, the proper tolerances, let's say. Then we need to have a fine mesh with high quality. This is why sometimes F7 to extend. This is why sometimes, yeah, the FEA stops and does not converge. Because what I'm doing live is mostly improvisation, and it can go so far, yes. Normally, any FEA topic should be studied for at least a few days or weeks. So this is the disk. This is the pad. The pad has the material called pad, and the disk has the material called gray cast iron. The contact is the usual friction coefficient between brake pad friction coefficient 0.3 to 0.5, yeah, 0.5. Frictional, yes, 0.5. Behavior detection method, nodal normal from contact. Let's let this side for the contact at this moment. Let's click here, generate mesh. And here, let's make it, I don't know, 2. It looks nice for the beginning. We have a physics region with everything. All right, as a load, I would want to have a reference temperature here and the convection. Control B, everything. And if we go here towards the meter, we can assign ten. Let's work with 10 and see where we go from here. We have two loads. One load is the rotation of the disk. At this moment, I don't want to put it here. Normally it should be here, but at this moment, I don't want it here. Let's assign it here. Body ground revolute. And because the rotation is above the z-axis, we are correct. Then we're going to press the pad onto the disk. How much should we press it? How much? Displacement, this is 0 and 0, and we'll displace it only with the minus something, I don't know, minus 0.025, all right? Let's assign the load, which is a joint load due to the revolute joint load. And how much? What should I? Let's find out rotational velocity. Brake. Car wheel rotational velocity. (800 RPM. Let's see what is 800 RPM in radian per second. 83. But nevertheless, I think we have 800 RPM here. Do we have RPMs? Look here, RPMs. Should we make RPM? 800. Oh my God, I think it's too much. I think it's too much. Because it's breaking, you know, let's make it a little less. I would like to have convergence, and sincerely, I would like also to compare with the previous simulation, and it has similar values, let's say. I don't want to waste a few hours to debug this simulation. All right, analysis settings. How much time should I give? I don't know, 5 seconds? 0.2, 0. Yes. Let's be a little more generous. And yeah, let's test it if it works. Right click, switch to automatic mode, and here on the solution I am going to insert such values, including temperature. And why not total heat flux? Displacement. Oh, let's go here with 0, right? 0, I said. Let's not repeat the problem that I had in the past. Minus 25, no. (0.025). Do we have a displacement? Like brake pad travel? No value? Why? Why don't you give me no value? Let's see how fast is it solving. What number of nodes do we have? 10,000. 10,000 nodes, all right. Maybe I should have used here solver type direct. Because it goes so fine, let's increase the minimum time step. 0.05, and we're starting with 0.1. Clear generated data solve, yes. And here I said solver type direct, and hopefully it will solve faster. Yes. Refined piston. Taper impact side. Yes, but I think you didn't use a nonlinear material, and also you didn't make a round. You should have made a round. IC engine. Show me. Yeah, bonded contacts. Bonded contacts everywhere. Here, here, everywhere. Absolute beginner. Rigid body dynamics, opposite piston and opposite cylinder motion study. Does he have results? Oh, this looks nice. Let me show it to you. Playback speed, let's make it 1.5. Yeah, it looks nice. Mechanical butterfly, oh. Yeah, nice work, Mr. Anuj Kaushal. This is the retracting movement. I'm looking here at the pistons. Here it works correctly. I don't know here what happens. Yeah, nice work, lots of work. Lots of work. Convert CFD. So this one retracting, oh my god, this looks so nice. Fatigue analysis of crankshaft. So let's see. Where is the problem? You know what? Let's decrease here. So nice. This is a mastercraft. Yeah. Does he have something more? Take this one. Yeah, dude, but you're showing only 0. Will something happen? Yes. Yeah, it looks nice. Mm-hmm. Yeah, nice. Analysis, come on. He's testing gear motion with bonded contacts. How can you test with bonded contacts? How? Oh, this is nice. This looks so nice. We have a faster playback speed. Yeah, it's nice. Oh, this is nice from Mr. Ahmed. With the segments, yes, I like this. Do we have temperature or only stress? Come on, show us. He doesn't show temperature. Come on, why? Oh, such a nice example and no temperature. Nice example, Mr. Ahmed. Finally, something nice. ANSYS rigid dynamics analysis, Scotch yoke mechanism. Foundation to expert in ANSYS workbench. Oh. Oh my God. By the way, we should change to ANSYS break because we are not on the piston anymore. It's a thermal simulation. Temperature and convection, yes. Look here, he is keeping separate parts. The ribs are separate parts, which is absolutely not correct, all right? It should be, they should be one body. All this should be one body. So nothing happened. What temperature do you apply? This temperature. And I think he didn't select the faces. Yeah, he didn't select the faces correctly. He has put so it's 12. It's a maximum of 12 watt per square meter Kelvin. Oh no, please, he didn't select the other parts. No, you shouldn't. This is why he has 0 likes. Come on. We're going somewhere. Let's see if we're on the right track. So it will not show results. Okay, it shows. Can we hope for some temperature, please? Yes. Yes, we can hope. Yeah, this is nice. We're on the rightest of the rightest tracks. Thermostructure analysis. It's a thermal thermostructure, yeah. Break disk. FEA versus test. Even though this is made in Abacus, I will show to you because it also has this movie with the infrared camera. In order to also know what is the end point of the simulation, it should be red. Okay. Here I don't know what is happening. It's not showing what it should. The value, he has filtered with the room temperature, this one, and it's this gray, which according to my taste, it doesn't look good. It should be something like this. Something like this, because the reality is red, hot red. But yes, it's nice. It looks very nice. ANSYS thermal tutorial. I don't want a thermal tutorial. Show me heat dissipation. What is this? According to my keen eye, I see a pressure, a joint, and yes, he has APDL commands. He is doing something, but he doesn't. The FEA stops just to see how much work is. Commands. This was made 5 years ago. Commands. This is why I'm showing you this method, which I think it's first time when it's shown on YouTube or everywhere. It's a very quick method, okay? No APDL commands, and it's very suitable for beginners. So besides the pressure in joint, another remote displacement, and the commands everywhere. Not for you, my spectators. You get the easiest way. So he's doing something, but the FEA crashes. He scopes for a temperature, and he has, yeah, it is a beginning, yeah. It's maybe the mesh is too coarse also. I will not look at the commands because I'm not an expert in APDL. But yeah, this is the beginning. And from now on, hours and days are needed to make it convergent, make it work, and show decent results. So yeah, the work is extensive. And he got almost 100 likes for his works, for his work. Does he have something more? Let's see if he goes where he should go. Here he has a different part, you can see. This is different from this one. Frictional, frictionless, rotational, all right, yes. And yes, it stopped here. This is the difference, ladies and gentlemen, between a beginner and an expert or a specialist or something. The beginner stops here. After a few more minutes of trial, he goes to sleep, all right? So he doesn't care anymore. Or maybe goes here, but I don't know if it's such a big difference between this. Yeah, it's a little thinned. The diameter is decreased, so I would give him that. Only, yes, he stopped, and there are a few more days of work. This is why on expertfea.com we present the results after the days and weeks and months of work. And believe me, it's a lot of work. To people watching, hello, people watching. Disc brake frictional heating analysis. I took inspiration from this person. He helped me with some APDL commands, yes. Many years ago. How much? 7 years ago. He helped me with some APDL commands. I kind of optimized it because you can see the temperature is not correct. It's too low. And I also introduced now a very good way, this one. Heat dissipation with coupled field transient, yes? Look here how nice it looks, and the proper temperature value, very nice. What is this structure? I don't care about structural. Coupled thermal stress analysis, he starts with the thermal, I'm not interested. ANSYS disk break analysis in transient. Do you have dissipated heat? Static model, static transient, oh my god. So much work. Import contacts. I hope you don't leave them bonded, I hope. Frictional, 0.7, all right. Frictional again. And what do? You revolve, all right. Look here, as I mentioned 10 minutes ago maybe, it's one part, yeah? Why did he make the ribs different parts? It's not possible, come on. It's laughable. Joint load, rotation 120 RPM, yes. And transient, will it rotate? This is my question. He's pressing 0.55. It's kind of much for my taste. If it's too much, it will create convergence problems. He also applied the pressure. And he stopped. Yes, he stopped. He stopped. No results. Does he have results? Why? Why should he have results? Huh? Why? Where is the break? This is the break. That's all. Does he have results? It's like a tutorial without results. Yeah, so it's half the work. It's not complete. Analysis of this break by fluent flow. Complete CFD. This break temperature rise. Simulation is done in ANSYS. Let's see, what has he done? This is correct. Yeah, this is correct. Even though it's too short, it's correct. This is one of my first trials, and yeah, I'm a little ashamed to show. But at least I mentioned this as a trial. This was made with APDL commands, and yeah, it was the beginning. This rotation. Thermal structure. ANSYS space claim rotary disc brake design. Thermal analysis, I don't care. Thermal structure, no. This is interesting. But here to define the R-card law, the where R-card where law, we need to use APDL commands. It's very nice. So we can see the pad, the brake pad being eroded due to friction. It's, yeah. It's like on a drum brake. Frictional heat generation during braking with convection heat loss. Oh, this looks nice. 100. Yes, he should go for a higher temperature, but it's nice. Yes. Nice work, Mr. Fernando. Modeling to improve your brake system. ANSYS display. ANSYS fluent. I don't care at this moment. Model analysis, because one can do model analysis. You don't need to. For model analysis, there are times when you don't need any boundary condition. The software will put everything, or it will take the part as is. No boundary condition. This bearing looks nice. Of disc brake by using ANSYS. How? Heat and flux, yes, but no heat, no friction. Yeah, I want heat dissipated due to friction. This brake analysis. Interesting wordplay. CAD with me. Muzzle brake simulation. What is this? Oh my god, it looks so nice. Yeah, nice animation. This brake is written differently. ANSYS fracture. We will also perform fracture simulations in one of the upcoming live streams. This I want to see. Mr. Adam, no. Brake system simulation with ANSYS. In sensing desirable user simulation, brake system design case. Yes. And yes, an advanced scenario with 2 brake pads instead of 1. This is, let's say, my iteration 1 year ago. And yeah, let's make it a little slower because the temperature looks so nice. This is stress, nevertheless, but we will see the temperature. This is heat flux. I filtered for more red in the animation. Stress on the inner side, on the lining of the brake pad. Finally, some temperature. Yeah, this looks nice. This is heat flux again. All right, yes. Very nice. Break. This is not break. Fatigue analysis on brake pads and brake disc. Pin disc wear analysis, our cards law. From our collaborator in the past. Does he have wear? This is the question. It's not a visible wear. There is some pressure, but not visible wear. He then blurred or faked some values here. Couple field analysis. This needs to be shown and seen. Where are we? 54. Second two. Can we make it run faster? Let's see the time increment. It's at the minimum, the lowest value here. So right now I will declare this FEA as fully working. And because it takes time, transient structural simulation takes time. In ANSYS and everywhere. All right, so we declare this as working, and I would like to play a little with the minimum tie step. Let me pause it. I would like to increase the time step, maybe to 0.1. All right, so yes, and let's maybe solve it fast if it works. If not, we can end the stream here, no problem. Do we have any question or something? No. You can also see there is no more questions. There are no more questions. Where were we? Here. Maximize. Done. ANSYS APDL. ANSYS APDL, while is the preferred tool of all the expert guys. Yeah, it's not, I will admit it, it's not user-friendly, and it didn't appeal to me. And yes, with it you can do almost anything and everything if you have the knowledge. ANSYS workbench is more limited. But in the end, my website is proof that we can also do lots of awesome work without APDL commands. Let's also decrease here, maybe make 3 steps. and here 0.07. Let's see if it works. If not, this is it. I think it will not work. Below 5 it will not work, I think. Sorry, above 5 it will not work, I think. It might work. I don't know. Let's see. So APDL, let's see, 50 watt per. Come on, why do you? Watt per meter Kelvin. This is the coefficient. All right, yeah, it's correct. Yes, quarter symmetry. Such a nice mesh. This is displacement. Does he animate? No. No. Do we have temperature? Stress? We don't care about stress. Show me temperature. We can see the limits of the symmetry. Where is the couple field? I don't understand. Where is the couple field? Because he doesn't show temperature. Yeah, no temperature. Stress, deformation. And where is the couple field? You said couple field, structure and term. Sliding mesh, CFD? What? What is this? Modeling of disc brake in Pro Engineer. Brake disc analysis by using. Yeah, maybe I was right with minimum. Let's make it 5. Clear generated data. Yes, save, solve. Best in kind. Here's thermal and structural. Learn how to simulate either current, breaking Schemer. Some Hindi here. How to ANSYS over thermal analysis of this break. Oh my god. How to ANSYS. degrees Celsius, because he assigned 1000 degrees Celsius. Pratt & Whitney relies on ANSYS simulation to achieve carbon neutral aircraft. Muzzle brake. What is this? Like a fatigue simulation, maybe. Coupled analysis thermostatic. Oh my god. Anyone and his mother have done coupled thermal structure. Oh my god. Old school brake caliper. Old school brake caliper. With here with the spring. Yeah, I think it's a nice structural simulation. If I remember correctly, I know these guys and they are doing nice work. Muzzle brake safety. Oh my god. This brake rotor. Brake disc simulation. Does he also simulate the caliper? No. He has no caliper, and in the thumbnail he has the caliper. Why? Why? This is lying, dude. This is lying. ANSYS coupled field transient analysis. Finally, something that looks correct. Yeah, this looks correct. Finally, out of hundreds of simulations. All right, hopefully soon we'll finish and we can end the live stream successfully. Disc brake structure thermal transient. Oh. Mr. Juraj or Juraj Uradnicek. He seems to be like Czech or Slovak. Juraj, I think it's Juraj, yeah. This looks nice. We don't know what it is. It may be also stress. Yeah, instead of temperature, because he is doing a nice zoom, a nice crop in order to not show what the colors are, but yeah, it looks promising. Electromagnetic brake. AI. What is this? Siemens Index. Let's see. It looks nice from above. This I made with the APDL commands. It's very nice. We can see it, why not? Given the amount of awful simulations that we've seen, we can also see some good ones. I think I have a very coarse mesh because the solving took too much time, I think. Let's see that solving. Second 3, second 4, second 5. Yeah, so we have around 5 seconds of real time, let's say. Pressure from the brake pad, something in the contact, penetration. It's cute, yes. Thermostatic frictional heating, including a hardware simulation. So let's see, heating and wear in the same time. Yeah, this should be interesting. It kind of stopped here. Let's see why. Out of curiosity, can we make a more coarse mesh? Let's see. So when we make the mesh more coarse, then we refine the minimum time step. Let's see if it works. So he has a beginning of a temperature, which is obviously not enough. And he has also some wear. The wear is defined with an expression. Yeah, it's a beginning. He's no, I don't know this guy. No, he took the FEA or purchased it. I don't know from this guy, or maybe this Dinhan. Maybe he has made a YouTube channel with the animations. Let's see. Let's see if all his videos are watermarked with Dinhan. Okay, sure. You know what? We should not go into detail because it's not our business. Range breaking summation. Transient thermal analysis. Finally, a caliper, but it's model, so it's not. Yeah, so zero effort because the only boundary condition is just a fixed support here in the middle, so not too much effort. ANSYS heart, brake directional deformation. Yeah, so this is how someone gets his or her heart broken or separated. This is new in ANSYS. What? He's reading? Or what? Here's a rotation. I don't know what is this, but it looks nice. Oh. Let's see it. Let's see it. This is made in. This will be a great tutorial. Yeah, this is a good beginning. It's not perfect, but it's a good beginning. He doesn't say what it is. Stress, strain, or degrees. Sorry, yeah. Degrees Celsius. It's a nice beginning. And it takes a lot of work. A lot of work. Rotor heat simulated with heat, yes. So no heat dissipated due to friction. What have we here? Yeah, it seems to work. Let's wait. This is interesting. What is this? This is like a bolt nut assembly. Simple bar analysis. 2D bar. Oh my god, 2D bar. This is made when? What is this? This looks so nice. So the minimum time increment is 0.025. And let me read. Suke Jensen. I think. Suke Youngson. Youngson. Go. So Ge Youngson. All right. Come on, what's with the awful quality? Your ANSYS Korea, you should have the top quality. Come on. 360 pixels 4 years ago? No, it's not possible. Please, no. No, not possible. is this? Escape chain. A bench, FEA of a bench. So make me understand. This guy has 55,000 views for a simple bar. I need to see this. I'm APDL, and I said APDL is unpopular. $55,000 views. So how many views does he have? 212. Hole in a plate, 5,000 views. Yeah. I can only envy him. 55,000 views. Let's go now if we have LS Dyno break. Yes. Oh. This cuts deep. This is interesting. No more breaking in LS Dyno, no more breaking. It stopped. Ooh. Oh my god. It's the same, I think. It's the... let's see how to restart. Yes, I modified the minimum time step. I am not modifying any of the boundary conditions. And here we will go for manual. And instead of initial, we are selecting the last. This is the last sub-step. Yes. And here we'll go for solve. Let's see if it, no, it didn't resume, unfortunately. So clear generated data, yes. Let's solve with this value. Yeah, this is top. I think he copied the clip from YouTube. And yeah, he's asking to learn how to also do it. Yeah. So we have only one LS Dyno break simulation and we don't know the author. Yeah, but I bet we have multiple Abacus simulations. I don't care about bake squill. I care about this one, temperature displacement. Let's see if this works. Terminus of this bake. What is here? Clear generated data. Yes, self. I will watch my smartphone for a second. Okay, silence. Basic brake disconnects. But no heating. Couple temperature displacement tutorial. It looks promising. It looks promising. It's nice, yes, nice. And where? With MSC products, McNeil-Schwendler Corporation, but they were purchased. MSC software was purchased by Hexagon. I remember because I used to work in the Nastran and Patran, and MSC, McNeil-Schwendler Corporation, had the rights. They were selling the official Nastran and Patran. Also Mark, Ditran, and Adams, MSC Adams. Come on, go, please. You see, it wanted below 2.5 E minus 2. It wanted this. So this is temperature. MSC Mark, yes. So this company was purchased by Hexagon a few years ago. What do they have? Do they have more simulations? Dynamic response. Adams, as I told you, Adams. They seem something like Malaysia, Indonesia, Philippines, something. Let's check the website just for fun. Indonesia, Ooh. Oh, maybe it was a firewall or something. The enabler behind every innovation. Yes. Theory CFD. Theories. What is this? Theory CFD. Tensor engineering. Tensor calculator. Let's see. This website. Online courses. They are the guys from this website because I've seen his face. Platform dedicated. This is the website. Engineering services, mechanical FEA. Just a simulation. Alright, so this guy, David, has made multiple simulations with this no results here. That's all. With the maximum here, which is not correct because it's nothing here. Nice try. Does he have results? No. Mr. Schorle, do you have results? No. Ah, maybe he has. No. No heat dissipated? No heat dissipated. So if it stops, then we are going to stop the live stream. Nevertheless, this simulation is available on our website. Feel free to, at any time, to search for whatever you like. For example, expert FEA break, and you will reach us. Here, with this simulation, and you have, look here, you have the link from where to purchase it. So, yeah. Nice. Very nice movie. Can we have a brake simulation? Why don't we see any rotation? Why? No rotation? Why? Electrothermomechanical simulation of eddy current braking systems in EMS for solid earth. ABS. something more interesting. All right. Oh, we exceeded the second two. So, what is this? Maybe it's made in console? Or, yeah, console multiphysics. Cathode, disc brake, this. Why? This is a disc brake simulation? Dude, you need to rename your... You need to rename your video. Maybe this is disc brake simulation, maybe. Or not? No? No. Fooling thumbnail. Oh my god! Does he do it on purpose? Brake heat transfer. There is some transfer, but yeah, it's only a thermal simulation. Is this the brake? No. No brake. Yeah, nice try. Is this the disc brake? No. I'm curious. Does he have a disc brake? He has a disc brake. Oh my god. He has a disc brake simulation. Finally. He has a disc brake. He's evaluating the results. What have we here? We have temperature in Kelvin. 120 degrees Celsius. But it's heat flux, thermal contact surfaces. It's not rotating, I think. Yeah. It's not rotating. So our simulation will finish successfully in 2 minutes. I'm interested to see a rotation of the disk. It can be because there is a gradient here. It can be that it rotates. I didn't watch the previous videos to see his boundary conditions, but it can be that it rotates. So yeah, great thumbs up from me. A battery pack here, battery pack. Brake dust. This is interesting. How to simulation disc brake model SolidWorks. This is casting of a pedal. Brake pedal. Two-wheeler disc brake simulation? What do you mean by two-wheeler? But it's nice, nevertheless. Duffel, parking brake, drum and head. Yeah, you don't see drum brakes. Did I make a drum brake simulation? I don't. Expert FEA drum brake. I don't think I made such a simulation. No. Oh, this is an interesting topic. I can make a drum brake simulation. Not that I didn't try it. Of course, I tried, and it's more challenging than the usual disc brake. I've seen this. Do we have something other software? MSC. MSC software, as I told you, they were purchased by Hexagon, as also ANSYS was purchased by Synopsys. No more than maybe 2 years ago, maybe. Yeah, until this part it looked very nice, yes. So our FEA is successfully finished. Let me see before showing the results if there is any question or something. No, there is no question. And yeah, let's evaluate a little the results. Let's make it 50 maybe. Or maybe 75 and 3 to keep the 25 frames per second. Velocity, what do you want? Stress. Yes, if we want, we can. Because I have applied the displacement from below, it's heavily stressed from here. The rotational joint, I applied it from below. It can be worth to be tested here to rotate it from the inside. What should I do here? Maybe 20? maybe 1. Let's filter it with 5. Yes. This is a quick solving. Oh, overkill. Quick solving FEA. How much? 300. So this is nice. The temperature, of course, is too high because we have too small gap, too high friction coefficient. Also, the convection coefficient, I think, can be optimized. But yes, this is how it looks like in principle. So feel free to optimize it and do similar stuff as we just did. Thank you very much for your attention, and we will see you in the next live stream. That's all from my side. Bye bye.